get started. So next we have Hamoon Mousavi from Columbia talking to us about a little bit more about non-commutativity. And this will be like, we'll take a 10-minute break near the end of the hour.
Sure. All right, so yeah, what I planned is to tell you a little bit about some of the rounding schemes that are available to us in when we study non-local games. But the class of non-local games that I will focus on are really special. They're coming from constraint satisfaction problems, classical constraint satisfaction problem. And because of this connection, I rarely ever evoke any language that we usually associate with non-local games. Here and there, I point out that, you know, underlying this, there is this non-local game picture, but that'll be all. But what constraint satisfaction problems, and why would they be interesting for us in quantum information, and what does rounding even mean in this context? So they will all be clear in the next few examples that I'm going to present. Okay? The first one is an example that most everyone in the room has seen before. It's the magic square game. It's the classical example of a constraint satisfaction problem where we have a 3 by 3 square. We associate a variable to every square, x1, x2 to x9, and they can take values in the set plus minus 1. And we have a bunch of constraints. We want the product of the variables in every row and column to be 1, plus 1, except that in the last column, we insist that the product be minus 1. Well, we all know that this sort of constraints are inconsistent, and we cannot satisfy them all simultaneously at once. And this is an interesting fact when you see it for the first time, that if we enlarge our domain, if we go beyond this plus minus 1 classical domain to the class of unitaries with eigenvalues that are plus minus 1, we can satisfy the constraints perfectly. So if we allow ourselves to use unitary, and throughout the talk, I'm going to show operators using capital letters and scalars using small letters. And if you require the rows and columns to multiply to I, except for the last one to minus I, and then we can satisfy these using unitaries. So we require that these be unitaries and have eigenvalues that are plus minus 1. Well, I mentioned to you that this is a game, but I didn't formulate it as a game. Let's just quickly do that. Most everyone has seen this example as a game. This is a game that is played between a referee and two players, Alice and Bob. The referee chooses one of the rows or columns and sends it to Alice, and also chooses one of the cells and sends it to Bob, and Alice and Bob must respond with assignments to the variables that they received. If they want to win, they must be consistent with one another, and Alice's assignment must satisfy the respective constraint row or column that she received. Now, by the mere fact that there's no classical assignment to satisfy these constraints, if Alice and Bob were restricted to classical strategies, if they were classical and wanted to win this game, well, their chance of winning is going to be strictly less than 1. Whereas if they were allowed to use quantum strategies, because of the fact that you can satisfy these constraints using observables perfectly, they can win the game with value 1. All right, so there are a few points that I want to make. First, that, this urge to try to plug in unitaries in this set of constraints was not just mathematical curiosity. The magic square game and this enlargement of the domain to unitaries has found really deep applications in quantum information, right? So it wasn't just mathematical curiosity. And the second point that I want to make is that it's a very good example of relaxation, which is going to be the topic of this mini workshop, like relaxation and rounding. So the relaxation, well, we had a set of constraints. We couldn't satisfy them. So we enlarged the domain, and we were able to perfectly satisfy it. And the relaxation always comes, precedes the rounding, which is the process with which we then take these operators xi and extract classical labels +1, -1 from them. Here it just so happened that the domain that we relaxed ourselves to was the set of operators. Or if we don't want to forget the algebraic structure underlying the domain, we might say that we relax to matrix algebras or rings of operators, right? If you want to insist not to forget the algebraic structure. But this is something, this type of relaxation to operator algebras was something that started happening when quantum information became a thing, right? Historically, you want to solve a constant satisfaction problem, the relaxation domain usually was a vector space. So this is something that this difference between vector space, relaxing to vector spaces or algebras will become clear as we go on the talk. All right, so my next example is also going to be super important. That one, most of you have seen it as this class of non-local games known as XOR games, the most famous example of which is the CHSH game. And, but I want to stay closer to the CSP kind of language. So I'm going to present it to you as this constant satisfaction problem known to us as max-cut. So I'm going to present it that way. And it's going to give us a recipe for relaxing any classical constant satisfaction problem to matrix algebras. Okay, so let's do that. Max-cut. An instance of max-cut is given to us by a graph. We are assigning a variable to every vertex of the graph, and these values, just like magic square, can take values in the set plus minus 1. And we have a bunch of constraints. Those constraints are that for every edge, we want xi to not be equal to xj for every edge ij. Okay? And max-cut simply asks, how many of these constraints can we satisfy all at once? Okay? Now, what would be a useful relaxation for this problem? Could we just say that, hey, just like max-cut, just like magic square, try to assign unitaries that have eigenvalues that are plus minus 1 and just require that these unitaries be different from each other. That's a little bit childish because you can always do that. There are infinitely many operators. You can always find distinct operators for every vertex. Really, the useful relaxation comes to us if we start thinking about max-cut as a polynomial optimization problem. So let's formulate max-cut as a polynomial optimization problem first, and then see how we can relax it. As a polynomial optimization, it's going to be as follows. So consider this expression, xi 1 minus xi xj divided by 2. Well, this expression is either going to be 0 or 1. And it's going to be 1 if and only if xi is not equal to xj. So if I sum it up for some assignment xi xj over all the edges, it counts the number of edges that assign different values for the endpoints, right? So this is going to be really, if we maximize this, this is going to be the max-cut problem viewed as a polynomial optimization, right? And let's spice things up and maybe add weights for edges as well. Okay? Now, we can do something similar to what we did with the magic square. Now we can ask, what would happen to this polynomial if we plug in unitaries with eigenvalues that are plus minus 1? So let's do that. Just, to be precise, we're going to maximize the trace of the operator that we obtain subject to the constraint that these operators are unitaries and they have eigenvalues that are plus minus 1. Okay? All right, the first thing that happens is that, well, this is really a relaxation in the sense that this inequality is true. Plus minus 1 are also unitaries. And, but for it to be useful, we have to answer two questions. First, can we solve this relaxation efficiently? And second, if we solved it and obtained this solution, can we can we round it back down to classical labels and obtain something that is going to be a good classical solution? Right? We have to answer these two questions. And well, the first one, the fact that this can be solved efficiently, is the content of what's known as the Tsirelson's theorem. And the second one, the fact that it can be rounded to a good classical solution, is the Goemans-Williamson's hyperplane rounding algorithm. Okay? And we're going to talk about these two things. But really the goal of this talk is to go beyond max cut and to see to what extent Tsirelson's and Goemans-Williamson can be extended. Our quest will be to find an approximate Tsirelson and an approximate Goemans-Williamson for problems beyond max cut. That's what we're going to try to do. But first, of course, we have to see the original Tsirelson and Goemans-Williamson, right? So let's do that. First, I'm going to present to you Goemans-Williamson. Not with all the detail. You've all seen it most likely before. So just going to very briefly remind ourselves what Goemans-Williamson was and remind ourselves what Tsirelson's was, right? All right, so I'm going to actually erase this because I want the board to be not a chaos as much as possible. So Goemans-Williamson set out to solve, first we are going to do Goemans-Williamson. They set out to solve this classical constant satisfaction problem. That was their goal. And the relaxation they chose was not the one that I wrote down. It was not to non-commutative world. It was to vector spaces. So they said, let's imagine these xi's now, instead of being plus minus 1, they are vectors with norm 1. Okay? And this problem is the relaxation they considered. And they, let xi's be now vectors and then relax the quadratic terms into inner products. It'll be clear once I wrote down this. Let's maximize over vectors of this expression subject to the constraint that xi's are norm 1 vectors. Now again, it should be clear that this is a relaxation, but we have to answer those same questions. Can we solve this efficiently? And can we, the answer to the first question, whether we can solve this efficiently, is a little bit easier than the non-commutative case, actually. This is not too difficult to see that this is a semi-definite program. And we can solve it efficiently so as far as we can solve semi-definite programming efficiently. So let me write it down as a semi-definite program, and then we can very quickly prove that this is the case, this equality holds. So this is maximization, like a linear function of the entries of a matrix X, where the matrix X is just an n by n matrix that is positive semi-definite and has 1 in the diagonal entries. And why the value of these two problems are the same? Well, one direction is very easy. This direction is super easy. If you have a bunch of vectors, a feasible solution, let's call this the vector problem, and this is the STP. If you have a feasible solution to the vector problem, then you can just form a matrix X from those vectors by just packaging those inner product in a matrix like this. I'm not going to elaborate, it should be clear. Like, you know, have label your columns and your rows by the vectors, and in every entry you would put the corresponding inner product of the column and row. Then you immediately get that this matrix X is going to be positive semi-definite, and the diagonal entries, by virtue of the fact that these vectors are norm 1, are going to be 1. So it's going to be feasible in the STP solution, and the objective functions are exactly the same. So it's going to achieve the same objective value as those vectors in the vector problem. And the other direction also is super simple, but let's also quickly see it. This other direction, if now I have an X that is feasible in this STP problem, I can always, from the fact that it's a positive semi-definite matrix, write it down or decompose it like this for another matrix V, and then obtain my vector to be just the columns of this decomposed matrix V. Now, again, from the fact that the diagonal entries of X are 1, we get that these are norm 1 vectors, so they're feasible in this problem, and they achieve the same objective value as the STP. So we can solve the vector problem efficiently. Once we obtained it, once we obtain those vectors, how can we round it back to those classical labels plus minus 1? Well, that's the hyperplane rounding. And let's also remind ourselves what that was. So if, for that, well, you obtain this bunch of vectors. You sample a vector R from the unit sphere, from the Haar measure on the unit sphere. And then you let the labels to be just the sign of the inner product of the vector R with every vector xi. Okay? So you obtain some random variables, and with a little bit of analysis, one can show that the expectation of this random variable here is going to be not too far from the analogous vector expression. This row here, this constant row being the Goemans-Williamson constant of 0.878. Okay, and this is the expression that shows up in our objective function, right? And this inequality immediately shows that the random assignment that we obtained from this rounding is going to achieve a value that is on expectation is going to be at least 0.878 times the STP value. Okay? All right, but what I promised to you was that there is a way to solve the non-commutative problem that I wrote down, and that there is a rounding for that, for that solution back to classical labels. So we will quickly do that, and then we move on to other constraint satisfaction problems. All right, so let me see how much of this. Yes?
How does the solution now relate to the optimal solution of the original problem?
Well, it's going to, so the max cut now is going to be at most the STP value, of course, and going to be at least rho times the STP value. So it's going to be sandwiched between, somewhere between. And you have a way of constructing a value, a solution with this quality. All right, so, and here is, let me not assume equality yet, but this was the non-commutative. Well, I didn't give it the name, but let's call it non-commutative Maxcot. And we don't want to confuse that with its cousin, quantum Maxcot, which John will talk about later today. And it was a problem of optimizing the trace of this polynomial. Okay, so I thought that there is a way to efficiently solve this problem. And and I told you the name of the theorem that does that. It's the Tsirelson theorem, and the content of which is just this equality. That this non-commutative Maxcot is really the same as the vector. The optimal value is the same as the optimal value of the vector problem. Now, one direction should be easy to see, like in the sense of proving it this by proving two inequalities. This direction should be easy to see because if we so I'm going to just rewrite this problem instead of trace. I'm going to just write it down as it's just the same as writing this as the Hilbert-Schmidt inner product of xi xj. But the Hilbert-Schmidt inner product really does not care about the operatory structure of these things, right? It just looks at the matrices as if they're vectors. So if you forget the unitariness, if you forget that they are operators, you recover really a solution to the vector problem. So this inequality should be obvious. This other direction is also not that difficult. So again, the strategy that we're going to take is as follows. We have a bunch of vectors, x1 to xn. From them, we want to construct a bunch of operators, x1 to xn, such that they are feasible in this problem. And if we can show that this operation going from vectors to operators preserves the inner products, then we have shown that this operator solution that we found is going to have the same objective value as the vectors in the vector problem. All right, so how can we do that? It's done through a special set of operators known as Weil-Brauer operators. So for every n, there's a bunch of special operators. Ryan also mentioned this in his talk. There are a bunch of operators sigma 1 to sigma n, such that they're themselves unitaries. They also have eigenvalues that are plus minus 1, and furthermore, they anti-commute with one another. Now the recipe for going from the vectors to operators is as follows. If your vector xi has these n entries, then you just construct your operator xi to be just the linear combinations of these special operators sigma I with coefficients that are coming from okay. Now, from the first two facts, from the first two properties of sigma i's, the unitariness and order 2-ness of these special operators, it's just very simple algebra to show that xi also would be feasible in the sense that it would be unitary and order 2. And also, using this third property, you can show that the inner product is also preserved. So that property I wrote down over here is also preserved. So that satisfies all our needs, and this construction does what we wanted it to do. Okay, any questions about this? Yes?
I didn't quite understand what the statement of Tsirelson's theorem was. Like, is it just that they're equal?
Yes, it is. It is. The statement is that. So I wanted to tell you that this can be solved efficiently. This non-commutative Max-Cut problem can be solved efficiently, and Tsirelson does it by showing that it is equal. Its value is equal to STP. And so that's what we are trying to show. Like I told you that this direction was easy because you can just forget about the operator structure and just get that. And then this other direction goes through transforming your vectors, constructing operators from your vectors, right? That will have this property.
And in the statement of the non-commutative max,
Yeah.
is there any constraint on the dimension of the matrices? Or?
There's no constraint, but from this construction, you can always, you always get something that the dimension is at most 2 to the n. Because we understand the representation theory of this algebra very well, right? And we know that there is always an irreducible of dimension 2 to the n for this.
So, and you said which properties are you using to show that this linear combination of unitaries are themselves unitary?
All three, actually. You have to use all three.
You have to use the anti-commutation.
Yeah, you use the anti-commutation. Yeah, good point. And Anand?
Oh yeah, like, I guess one difference from this morning is that you have the trace now enough to think.
Absolutely.
Lambda max. Like,
Yes.
I don't know, is there anything interesting to say about this problem but with lambda max instead of trace?
Yeah, so, there is this way of looking at this problem also as a game. I mentioned that some of you have seen it as an XOR game, right? And if you do it that way and you allow eigenvalue, maximum eigenvalue here, then this optimization problem is going to be giving you the quantum value of that associated XOR game.
But that's if you have commutation. That's if you have a bipartite structure.
That's if you have the bipartite structure between Alice and Bob. Right, yes.
You literally have this.
Yeah.
Maybe it's not even natural because like xi exchange
Right.
is not even Hermitian.
Yes. And you might, and you notice that the problem that Ryan wrote had a worse approximation ratio than, like this, in fact, you can solve efficiently, right? Whereas that one was like 1 over log n of like, STP. And so it could be because it considered the eigenvalue, right? But we're going to see that this trace approach is going to be closer to, if our goal is to solve the classical thing, this seems to be also interesting, or like,
And the trace is always like smaller than lambda.
The trace is always smaller than eigen, because it's going to be the average of the eigenvalues. Exactly. Yes.
So you solve the right-hand side with these exponentially large matrices.
Yes.
But they are, of the specific structures, they have succinct representation.
They have, yeah.
Is it going to be the case that the solutions will always be these very large matrices?
For other,
And will they always have succinct representations, or?
right. So if we restrict ourselves to Max-Cut,
Yeah.
you can expect that you would lose a little bit of, you lose a little bit of value, and you can realize it over polynomially large matrices instead of exponentially large. That's just doing some metric embedding type of things. Yeah, exactly. Yeah. But no, we know that to achieve the exact value, you're gonna need to go to exponential size matrices.
But I could always, if I just wanted a small approximation, I could just.
Yeah, exactly. You can up to polynomial size matrices. Polynomial being like the n number of vertices of the graph. Yes.
I think I missed it. I just want to, are you using like the normalized trace?
I'm using normalizes. Thanks so much for bringing that up. Yes, exactly. Yeah.
Sorry, what does the sigma I look like?
What does sigma I look like? Well, there is a way to construct them. It will take us a little bit far from like what I have planned for the talk. We are going to see actually generalization of these things when we move on to other constant satisfaction problems. And there I will tell you a little bit about how we produce the representation. But it's not too difficult. It is arranging the Pauli operators in a special, it's going to be tensor products of Pauli operators arranged in a way that you would achieve this. Pauli operators would always either commute and anti-commute. So you want to choose those elements of the Pauli operator that just anti-commute with one another, pairwise.
Okay, so their form is the product of powers. Each one is a product of powers.
Yes, yeah, each one of them is a tensor product of powers.
Yeah,
Exactly.
rather than
Yes. All right, so let's now try to see. Okay, so we saw that Tsirelson answered one of the questions. The other one is also incredibly just exactly like, what was the other question? Let me remind you. The other question was, now that we have the non-commutative solution, can we extract from it classical solution? Well, this point is a little bit moot because I told you that these two problems are the same, and I already told you how to round the vector problem to the classical solution. But bear with me, there's a point why I try to kind of formulate it this way, right? So, but that rounding scheme that I already gave you for by Goemans-Williamson is going to give us a way to round this non-commutative solution also to those classical labels. Let me write it down very quickly. So again, it's exactly just as before. Just choose R uniformly at random from the hypersphere, and let operator R be the linear combinations of these variable R operators. And then, just from the fact that this let the rounding be just like before, and just from the fact that this kind of transformation, going from vectors to operators, it preserves the inner product, you just have, you just recover the Goemans-Williamson, and just from the same analysis as before, you can get that expectation of this random variable that is important for us because it shows up in our objective function is going to be not too far from the operator value, the operator analog of the expression. Okay, so there's nothing magical that I'm saying here. It's just but I phrase it in terms of operators because we want to. I told you that we want to generalize or attempt to generalize Tsirelson and attempt to generalize Goemans-Williamson. So let's. It might be useful to have this operator view. Okay.
I'm sorry. So here there's these operators, the special operators you have.
Yep.
This would be playing the same role as the orthonormal basis for the.
They do. Yeah.
Yeah. So can you say a little more about in what sense they do? Why is that?
Yeah. This property that we wanted, that x, y, to be the same as the vector x and y. This one really relies on coming up with a basis sigma 1 to sigma n. Like if x and y are just linear combinations of some sigma I sigma n, right? As long as the sigma i's are orthonormal, form an orthonormal basis for the set of matrices, then you have this property. And they do satisfy that, right? Because of this.
Yeah, exactly. So I was hoping, I was just not seeing it off the top of my head.
Exactly.
Why does anti-commutation correspond to orthonormal?
Yeah, because if I take the trace, if I imagine trace, if I just take the trace of these two, then by cyclicity of trace, I would get that this is sigma I sigma j, and so it must be 0. And so by in Hilbert-Schmidt inner product, it has to be orthonormal. But that's not all sufficient because we don't want just up to trace to have this anti-commutation, or we don't want just orthonormality. We want really the structure of this algebraic relation because that is going to be what we need to prove that the xi is unitary and order 2, right?
Sorry, there's something else I missed. It's sort of a naive question, but I would imagine one goal here would be, look, you had a relaxation in vectors, and then you say, well, look, but maybe we want a better relaxation.
Yes.
We want more constraints. So this, this structure, the algebraic structure, has more constraints. And then Tsirelson is coming back and saying it's disappointing, once you have
exactly
large dimensions, it's not. So was this a disappointment, or was it a
Okay, so in the case of Max Scott, we were actually not hoping that this non-commutative approach is going to give us a better approximation because up to unit games, conjecture, this ratio that we have here is going to be optimal. Okay, so we were not hoping to gain something from the non-commutative max cut. But the moment we move on to constraint satisfaction problems that are not max cut, the picture is not as clear, especially when we don't have the unique game sharpness of the approximation ratio, right? But we still wanted to kind of motivate it through max cut because everything is just clean and everything just is working out. But yes, it's disappointing that it doesn't give us something larger. But another way that I motivated it was that this value here is already super important anyway in quantum information because this is the quantum value of a synchronous. This is the synchronous value of the XOR game that arises from this max cut instance. So all of these non-commutative problems that I'm going to write down, underlying them, there is a non-local game, and that polynomial optimization is giving you exactly the quantum value of that non-local game. Whereas the classical polynomial gives you the classical value of the. All right. Let's. All right, so we want to generalize this, and so what kind of constraint satisfaction problem are we going to consider, right? So let's. There is a large family of constraint satisfaction problems that contain max cut and also unique games and some, some other problems. But among them, like I just wanted, choose one constraint satisfaction problem that is not max cut and on which we can apply some of these ideas. So I chose max 3 cut because it's already super close to max cut, right? And would get us there. We can use it as a vessel to apply these ideas. And so max 3 cut, again, every instance is given by a graph. We associate to every vertex a variable, but this time this variable, instead of taking binary values, they're going to be one of 3. They're going to be, like here I chose 1 omega and omega squared, where omega is the third root of unity. So the options here are third root of unity, okay? And constraints are exactly the same as max cut. We want xi to not be equal to xj for every ij. All right, let's take this and try to see how much of the story we can push forward, okay? And first we want to focus on Tsirelson. So first we want to understand whether we can solve the non-commutative analog of this problem efficiently. Then we worry about whether we can round it back to a classical solution. Okay, in the second part of the talk, as much time, as much as I can. So we know the drill. Yes.
So it's a very basic question.
Yes.
But when you were describing the optimization earlier in terms of the operators and the max cut.
Yes.
How did you ensure that the objective is a real number? Because you had and things like this, it wasn't always.
Right. So yeah, we can always assume that the objective function is real because we were taking trace, and the matrices were Hermitian actually. Because maybe I should have wrote it down like that because we wanted unitary and we wanted these two conditions. So this forces the eigenvalues to be +1 and -1, and it's going to be already normal, so it's going to be Hermitian, right? Yeah. That point actually was going to be even more important in the case of max 3 cut, whether the solution will be real. All right, all right, we know the drill. We know that we have to write this as a polynomial, so let's do that quickly. The expression here will be a modification of what we saw in the case of max cut. So this expression here for every edge ij, and here a star is just complex conjugate. When I put it on a scalar, it's a complex conjugate. When I put it on a matrix, it's Hermitian conjugate. So this expression here is going to be either 0 or 1 when xi's are these values, and it's going to be 1 if and only if xi is not equal to xj. Okay? So again, just like before, if I sum up all of these with the weights, hopefully you don't confuse this with omega, and maximize this, I'm gonna have captured the max 3-cut problem. Is it clear? Hopefully it's, so this is just very similar to what we did for max cut, and let's just quickly go and write down the non-commutative analog. So non-commutative max 3-cut is going to be this polynomial optimization. So just like before, instead of plugging in third root of unity, we want to plug in unitaries that have eigenvalues that are third root of unity, right? So yes.
Quite follow here. So you're maximizing some complex number here now?
Oh no, this is going to be real because so it is.
It's the same.
It's the same. Yes, exactly. Yes. This is just playing the role of ixj divided by 2 in the case of max cut, where xi's were just second root of unity, but now it's the third root of unity, so we have a complex conjugate. And all right, so this is going to be like we are maximizing the trace of this non-commutative polynomial. Now we have xi star xj. Hopefully these x and xi and xj are capital enough to show that they are unitaries. They're operators subject to the constraint that they are unitaries. And now we want them to have eigenvalues that are third root of unity, so we just want them to be order 3, right? That's okay. All right, so this is the problem that we are trying to solve. And again, there is a non-local game behind it. We don't need to, kind of like elaborate on those anymore. But let's do as much as we can, just like what we did with Tsirelson and max cut. We can write down a vector problem also associated to max 3-cut. Let's also write that down very quickly. Maximizing, so 2 minus vectors Now I'm not going to elaborate that this vector problem is an STP. It's exactly like the argument that I gave in the case of max cut. But what is its relation to NC max 3-cut? Should be clear that it's somehow related, but like what is the relationship? Well, again, just like before, if you forget the structure, the operator structure, we immediately get this inequality. Okay? And if we had Tsirelson, we would have had the equality. But we're not going to be able to have Tsirelson. There are very simple instances of max 3-cut where this inequality is strict. Okay? So we cannot hope to get equality. All right? But again, let's try to push as much as we can, just like in the case of max 3-cut. So we can solve this very efficiently. So we have these vectors x1 to xn. Maybe I should go to the other side of the board. So I have these vectors x1 to xn now, right? And I hope that I could find some special operator sigma 1, sigma n. We will see what they might be. But just doing the same drill as before. We want to be able to construct these operators xi from the vectors so that they are linear combinations of these special operators sigma i's. In the case of max cut, they were Weilbauer operator. They satisfied all our needs. But so what are some properties that we need to have for these sigma i's? Well, a moment of thought shows that if we want, first of all, one of our requirements is that we want xi's to be unitary. We want these xi's to be feasible here, right? So we want them to be unitary, and we want them to be order 3. And we want their inner product to be as much as possible close to the inner product of the vectors. Right? We saw that in the case of Maxwell, these were important properties that we needed. These two are essential. We need these two, unitary and order 3. All right, so if we want this unitary and order 3, we immediately get that the sigma i's must themselves be unitary and order 3. So let's write down the properties that we want from sigma i's. Sigma 1 to sigma n. The first property that we want is that we want them to be unitaries themselves. We want them to be order 3. It's not too difficult to see why we need these two. Because, so I want xi to be unitary and order 3 for any vector xi, right? So I can just imagine vector 1, 0, 0, 0, right? And that's, so I need this to hold. But I also need xi to be unitary for any sort of vectors that I would choose. Like not any, but like, vectors that their norm 2 is 1. That the unit norm vector is xi. So for that to happen, I'm going to need something that is going to look like anti-commutation, but it's not quite anti-commutation. Just exactly like the Weber case, if I want xi's to be unitary, I'm going to need this algebraic relation. There's no question about that. This, if you do the algebraic manipulation, you would have to need that this sort of anti-commutation must be true. It's different from anti-commutation because we have this adjoint operator here, right? And something that I'm going to write down 3 prime, because we also want order 3. And for order 3ness, again, doing some algebraic manipulation, you want this homogeneous polynomial. For order 3ness, you want this extra algebraic relation. All right, so this seems a little bit weird, but this is closer to what we in quantum information would be familiar with. Because one way to satisfy this strange-looking condition is to enforce that sigma I sigma j is equal to omega sigma j sigma I. Its almost canonical way of satisfying this would be this. Okay, so again, both here and here we have some modified anti-commutation. Let's call them exotic anti-commutation, right? So there are two exotic anti-commutation at play. Now, I wrote down for you an algebra presentation. I wrote down a set of generators and a set of relations. Does this algebra exist? Well, of course it does. I wrote down the presentation. That's the important question to ask is whether it's interesting, whether there would be a representation for this algebra that is non-trivial. Well, the answer to that question is a resounding no. We cannot do that. Because there are multiple ways to do that, but playing with this relationship or just writing down the Grobner basis for the ideal generated by these relationships, you would get that 1 must be equal to 0 in this algebra, which means that everything in this algebra must be 0. So it's the zero-dimensional algebra. So it's not interesting. And the reason for it is that these two relationships, these two exotic anti-commutation, are inconsistent with one another. If you sacrifice one of them, you can always build representation. So for example, if you sacrifice this one and just want to achieve this one, this is going to be generalized Pauli operators, the clock and shift construction. And we're familiar with that. But this one, if you forget this one and want to satisfy this one, that's a little bit less familiar. But for example, when n is equal to 2, this is the group that is going to generate forget about the algebra. The group that sigma 1 and sigma 2 is going to generate is going to be the alternating group of degree 4. And we understand its representation very well. And we know that it has a non-trivial representation. And that satisfies this. So, and in fact, this is true for all n. If we try to kind of sacrifice the 3 prime, we would be able to construct representations for this. And I may talk about it a little bit later. So now, and we kind of knew that this is going to happen. We knew that we're not going to be able to satisfy all these things because I said that this inequality here is strict, right? So something has to give. We are designing an approximation algorithm, and this is the place that we have to sacrifice something. So yes, go ahead.
Clarify that. So like the reason that's true is that if all 1, 2, 3 prime was true, then you would have exact equality of the inner products.
Exactly. You would have this. And you would have unitary, and you would have order 3. So the solutions that you got, the vector solutions that you got, you can transform them to operators, and their eigenvalues. The inner product is going to be exactly the same.
I see. So if I drop the inner product condition, but just want to be unitary and order 3, like how does that change the conditions I do with the sigmas?
Oh, actually, so I didn't even worry about this at all. This comes automatically. Like this is in fact satisfied even if I forget this one or if I forget this one. In either case, I would get this. This only relies on the only thing we need for this one is that these are orthonormal matrices. And we can do that. Okay, but satisfying these two or satisfying these two properties is the difficult one. So I have to kind of satisfy, like if I forget this one, I'll be able to get for free that xi's are unitary. But then in my rounding, because I'm designing an approximation algorithm, right? I'm going to get xi that is a unitary. Now I'm going to have to find a way to round it down to a unitary that is order 3. Yeah. And if I forget about this, and if I sacrifice this one, then I have to. So maybe this is a good time to take that 10 minutes break. And then I can continue with this. Okay. So we saw that we have to sacrifice something, so that's the thing. That's the interesting thing that happens when we want to solve a classical constant satisfaction problem. We didn't have to make this choice. We usually just relax to vector spaces and that's it. But here we wanted to solve a non-commutative optimization problem. We have to kind of choose what algebra we want to relax ourselves to, right? So we had a choice, for example, here. So every problem would afford you some choices, and you have to make this decision. And each one that you make is going to give you a different approximation ratio, a qualitatively different approximation algorithm. So here we wanted to have this ideal scenario where we would have all these properties so that we would have all these other properties here for xi, and we saw that we couldn't. But a beautiful thing happens. If we imagine we take 1, 2, and 3, or maybe I can just keep using the blue. If we keep the properties 1, 2, and 3 and just sacrifice the 3 prime, we are going to get for free the unitary xi. But then we may ask, okay, how close is this to an order 3 unitary? It turns out that it is very close. So if you, for example, your xi is just a linear combinations of the sigma j's. If you choose this vector at random, and if you look at the complex plane and the unit circle, you're going to see that the eigenvalues of xi's are going to be scattered around the third root of unity. If they were third root of unity, we would have had order 3 unitary, right? So depending on how well you can prove such a statement, so another choice that you have to make is this metric for closeness, right? You sacrifice the order 3-ness, but in some metric, here I'm suggesting Frobenius norm, because I'm talking about the eigenvalues, you would be close to an order 3 unitary, right? And so you have to make a choice. And we're going to see that it's going to affect our approximation ratio. Similar thing happens when we sacrifice the unitariness and get only the order 3-ness. Then again, linear algebra just like here, would tell us a way to round it to a unitary that is order 3, right? So for example, like, I mean, I can do this quickly, like if xi has the singular value decomposition that is u star dv, where d is a diagonal matrix and u and v are some unitaries, you're guaranteed by linear algebra that if you forget about d and just write xi as u star v, this is going to be the closest order 3 unitary that you could possibly find in Frobenius norm to this order 3 operators that you had that originally wasn't a unitary. Right? So linear algebra is going to provide you with these ways of like doing your rounding, right? You know, this was up to the Frobenius norm. So maybe that is a good choice for the approximation algorithm that you want to design. Maybe it's not. So let's make a few of these choices and come up with an approximation algorithm and analyze it for max 3 cut, right? So, yes?
So I'm still stuck on your condition 3, because you say this is xi is unitary, but isn't 1 that xi is unitary? How is that related to
So I said that you almost certainly have to get these two relationships,
yes.
right? From the fact that you want this to be true for any vector. So in particular, if your vector xi is 1, 0, 0, 0, right? It means that the operator that you would get, this xi that you constructed, is going to be sigma I, sigma 1 in this case. And so if you require xi to be unitary and order 3, then sigma I must be unitary order 3. So these two you get from special choices of vector. And then if you want this to be true for all vectors, then you have to have this property. But good question, thank you. So now, all right, let's go with these choices that we have here, 1, 2, 3. We get the unitary. And unfortunately, the linear algebraic approach is going to give you an approximation ratio that is going to be slightly less than what I am going to present to you here. So, so I'm going to present you the better approach, okay? Here, and it makes sense because there's nowhere here we said anything about Frobenius norm. So it doesn't make, kind of like, anyway, maybe, kind of like you have to be smart about choosing the metric that you want. Like you sacrifice something, you want to know how close you are to that thing that you sacrificed. That closeness you have to define in a certain way. And we're going to see it now. So we had a unitary xi. And we want to get an order 3 unitary from it. So we want to round it to an xi hat that is order 3 unitary. In this rounding procedure, we do the following. We say send xi to this slightly bigger matrix constructed as follows. It's a deterministic rounding algorithm. You have the xi, you produce this bigger matrix. Yes?
So just for the linear algebraic approach that you mentioned earlier.
Yes.
So you replaced D when you took the SVD. You took
Yeah.
the SVD
Yeah.
to replace D with the identity. Did you mean
Yeah.
to say replace D with, you look at the diagonal element and you replace it with the closest root of unity?
Oh, that's the other. So if you preserved unitariness and you wanted to get order 3,
Yeah.
that's the approach that you take. Yeah. If you had order 3 and you wanted to get unitary, you have to forget that D completely and replace it with identity. You can prove this, that this is up to Frobenius norm. This is going to be the closest order 3 unitary to you. But here we took the unitary approach, so the thing that you mentioned is going to be the way to do it. So you just look at the eigenvalue in the spectral decomposition, you just find the closest root of unity to it. And that's it. That's going to give you the operator that is order 3 unitary. But that is going to give us something that is a slightly less in approximation ratio in here. All right, so this is a very simple exercise that if xi is any unitary operator, if you put it this way, you are going to get an order 3 unitary. This is the clock and shift that we are familiar with. And all right, so this is, let's call it xi hat. That's it. That's our rounding. Unlike Goemans-Williamson, which was randomized, this is deterministic, and we're going to analyze it. We're going to analyze it and try to find out what is the approximation ratio. Okay, let's do that. So, Maybe I can do it in this little space here. So analysis. So what is important in the analysis is to be able to calculate the trace of this xi star xj. Well, one thing that I didn't mention to you is that because this is Hermitian, we can always assume that in any optimal solution, these xi's, these vectors, are going to be real. So don't worry about that these two inner products would have different values or be conjugate of each other. They're going to be the same. They're going to be real, and the same thing here. The trace of this guy and this guy are going to be the same. So we have a real structure. So the trace of this guy is going to be xi, the inner product of xi xj. Sorry, and this is the one that we want to calculate, the rounded operators, the feasible solution. This xi hat is the feasible solution here. Now, this inner product is very easy to calculate. 2/3 of the time, it's going to be the inner product of xi xj, and 1/3 of the time, it's going to be this, let's call it garbage. Right? Which makes sense because 2 out of 3 of the entries of xi hat are xi, and one of them is the garbage. And if you take this inner product, it's a simple exercise that you would get this. Okay? And now, if it was the case that xi was unitary, and it is unitary. If it was an order 3 unitary, let's call it 3 unitary. If it was that, then xi star, xi minus, xi raised to the minus 2 is going to be just xi. Okay? Then this inner product would have been just the same as the inner product of xi and xj. But we know it's not the case. In reality, this is not. It's just a unitary. It's not order 3. But those things that I mentioned, like for example, if you plot it in, plot the eigenvalues, you're going to see that you're going to be close to roots of unity. Well, we expect this xi to be close to being order 3. Okay, and here is the metric with which we're going to measure this closeness. So we want. What we want from for this proof is to show that, well, this guy is not going to be equal, but we want it to be close to what it would have been if xi's were unitaries. Okay, sorry that I'm trying to give this as a tutorial type of thing so that like we can apply it to other problems, and so it's kind of like applying this attempt and like that was Frobenius and it fails, and now this other approach. So now, this is in fact something that we have. It just turns out that this inner product is really xi xj. Well, it's not exactly xi xj, but it's xi xj squared. Inner product of xi xj squared. This doesn't completely follow from this algebraic relations of the sigma i's. It follows from the representation theory of the algebra. Okay, maybe I can say a few words later on about that, but it's not a difficult thing to prove. But it follows from the representation theory of that algebra, not just from those algebraic relations. So you cannot just look at this and try to hope to prove that this is going to be true.
So there can be another representation where it's tighter?
Not choosing this algebra. If you choose this algebra, which let's call it, I didn't give it a name. Let's call it generalized Walbauer, GWB, okay? Which is the name of a bridge in New York, so. And but if you trust that this is true, then we can prove a very good approximation ratio. Let's do that. So now.
Sorry, can I ask the same question I asked last time?
Yes.
So for these generalized algebra, can you give me the structure, vaguely the structure?
Oh yeah. Absolutely. Will you give me a moment after this? I'm going to get into how to construct the representation of this algebra. Essentially, it's going to be very much similar to what we saw with Walbauer. Pauli group is going to play a very important role. eval-bar were just Pauli operators, just especially selected Pauli operators that anti-commute with one another. Here, well, it's going to be a subgroup that is generated by this group.
Is it still going to be in product form?
The Paulis are going to be just, how do you construct tensor products of Paulis, and you would get the larger Pauli groups. Like for any number of generators, you have a Pauli group Pn, right? And which is constructed from the previous one by a tensor product. So that's exactly the kind of structure that will happen here, but in a subgroup of this one. Let me say a few words after we are done with this one. So now let's finish the analysis. Hopefully it's okay if I write here. So this is what we are trying to this is the expression using this quadratic law here and everything else that I mentioned. This is going to be 2 minus 4 over 3 xi, xj, and minus 2 over 3 xi, xj squared divided by 3. But these operators are orthonormal, again, from the representation theory of this group, this algebra. So the inner product of the operators xi, xj that are constructed from as to be linear combinations of these special operators is going to be the same as the inner product of the vectors. All right, so we are getting closer and closer to this form, okay? But we have a quadratic term, but it's a simple exercise. This quadratic polynomial in the inner product can be decomposed to be this expression here. I'm going to write it STP times one linear factor is going to be this one, and the other linear factor is going to be 1 plus 1/3 of the inner product xi and xj. 1 plus 1/3, okay? But now, something that I didn't tell you is that in any optimal solution of the vector problem, you can always assume that the inner product of two vector is at least minus half. This is not too difficult to show, but this must hold. In any optimal solution, you can always assume, I mean, there could be optimal solutions that this doesn't satisfy, but you can always get an optimal solution for which this is satisfied. So if we apply that, we get that this term is going to be at least 5/6. And so this is going to be at least 5/6 STP. So all in all, we proved that remember I said that I don't want the board to get chaotic? Well, this is what I meant. We get that NC max 3 cut is at most the value of the STP, and at least 5/6 the value of the STP. Okay? That's what these choices that we made is going to get us there. This is a deterministic approach. We have a randomized rounding approach that we have still not fully done with all the details, so I'm not going to present it here. But we think that that is going to achieve 13/15 approximation ratio. And I'm willing to conjecture that that is this 13/15 is the integrality gap of this non-commutative STP. Like meaning that there is an instance for which you cannot go beyond 13/15. The best that you could hope for would be 13/15. All right, so, and there's no reason to stop at max 3 cut. There is this large class of constant satisfaction problems. Yes?
So then, is there a way to compare the value of NC max 3 cut to the value of the integral optimal solution for max 3 cut?
Yeah, well, they would be different STPs, right? So.
I mean the actual value for the integral problem, max three cut original problem.
Yeah. Yeah, so that integrality gap is, I believe, like something around 0.83, 6, something. Like, okay, so there is no integrality gap proven for the max 3 cut, classical max 3 cut, in the sense of like, the one that we have from max cut, okay? The best that we could hope for to get for the classical problem is 0.94 up to NP completeness. But this is the best that we have, I guess.
When this was the approximate Tsirelson?
This is the attempt to have an approximate Tsirelson, exactly.
Okay, but you have to also tell us about the approximate Goemans-Williamson.
Yes, which probably, yeah, I wouldn't be able to, I have to. But let me just cut the corners of this one, and then, okay. So here is what happens. This was for max 3 cut, but you can imagine max k cut. For that, you would need sigma ik to be identity. Or you can imagine also this class of problems called linear unit games. So in general, you can apply this method to this framework to devise approximation algorithms. So for example, for max 4 cut, the approximation ratio that, following all of this, the approximation ratio that you would get would be 0.84. So in general, you can imagine this class of constant satisfaction problems. So what are they? Let me just quickly. They are constant satisfaction problem with a bunch of variables that would take values in some finite field, okay, and they would have some linear equations and linear inequation as their constraints. So they would be like things of this form, or inequation not equal to C. Like for example, in the case of max k cuts, we have the inequations, okay. And so these are in some finite field, and this class would contain like a bunch of problems, like all the max k cuts, all so-called linear unit games, and so on. All right, so now. So I gave you the example of max 3 cut, but you can do the same kind of a story for other constant satisfaction problems. And right, I want to talk about the representation, right? So how would you show that? How would you prove that there is a representation for this algebra that is non-trivial? Okay. So let me maybe finish by saying a few points about that. All right. And then we can have a half an hour of break.
Can I ask a quick question?
Please, yes.
So in the vector program, you have this fact that x, the product, or xi and the product xj has to be greater than -1/2.
Yes.
Is this something you also have a constraint to enforce in the non-commuting program?
So in fact, you could do that. You could imagine that the entries, that the inner product of these xij's are going to be at least -1/2.
Okay.
Yeah.
I guess what I'm wondering is that implied by one of the constraints in the algebra?
No, it is not implied. So one way to see it is the following. If you, so this STP that I wrote down is the first level STP relaxation of this non-commutative polynomial optimization, okay? If you go to the second level of this STP, you are going to get you're going to have a larger moment matrix, and you want that to be positive semi-definite. And there is a minor of this larger moment matrix that also has to be positive semi-definite. If you focus on that, it's a 3 by 3 matrix. You're going to get that the inner product of xi, xj in any optimal solution must be at least minus half. If you write down the second level of the relaxation. Okay, so that's one way to see it, but there is a geometric way of saying it as well for the classical case. But
so I guess it's just implied by the PSD.
For us, yes, it implies from the PSD. You know, here we wrote down the first level STP, but we borrow one little constraint from the second level STP, which forces any solution to be like that. The first level STP doesn't see this.
Yeah.
Right? The first level STP doesn't see this, but because it follows from the second level STP, you can always take it back and enforce it on the first level STP.
Yeah.
Okay. But in the classical case, you don't even in the vector case, you don't even need this STP business to get this. Just by virtue of the fact that you want to be able to, at the end of the day, round to third root of unity, you can always assume that these vectors would have inner product that is at least minus half. As for constructing representations for this algebra, it's usually easier to think about representation theory of groups, right? So let's think about the group that is generated by these generators and relationships. Well, we have a bunch of things that are not, in the language of group, like what is this adjoint and what is this minus, but still let's try to kind of like put some of these relations. So we want them to be order k, and we want them to have this exotic anti-commutation, right? So I can write it as this, and then minus sigma j inverse sigma I. That's it, right? But then this minus 1 is a little bit of a problem. We don't have that in a group, right? So, but this is something that we can easily deal with. We can just add an extra generator j, and let that to represent minus 1. And since we want it to be minus 1, we can add the relation that j squared is 1, okay? And that, well, minus 1 commutes with everything, so you want sigma j to commute with everything. All right, so if I can show that this group, this presentation of the group has a non-trivial representation, and what do I mean by that? If it has a representation that sends j to minus I, then I have proved that this is going to be the group algebra of this group. So I have constructed a representation for this algebra, okay? So how would I do that? Well, there are two key things in the proof of the existence of representations of this G. And they are the following. If one focuses on this subgroup generated by sigma I inverse sigma j inverse sigma I, you already see that they have this anti-commuting relationship with one another. But it's not going to be true that everything that is generated here is going to be anti-commuting with one another, right? Some of them are going to commute, some of them are going to anti-commute. But they're going to commute or anti-commute. And this is the property of Pauli operators. The only group that does this is the Pauli group. The only, like if you write down these algebraic relations that you want to satisfy, you get a group, and the only representations of this group are the Pauli matrices that we are familiar with, the only non-trivial, right? So G0, from this observation, you can show that G0 is isomorphic to the Pauli group. Yes?
Wait, so G0 is like generated by all those things from all IJ pairs, is that right? Or are you fixing an IJ pair?
For all IJ.
So
Good
why
question.
is it true that like sigma I inverse sigma j like commutes with sigma j inverse sigma k? Like, is that obvious from your relation?
Oh, it doesn't. It either commutes or it anti-commutes.
Oh, but even that fact that
Yes, because you can write down sigma I sigma j as sigma I inverse sigma k inverse sigma I. Right, so you can...
sigma j maybe, yeah.
J, exactly. So if you have something else like sigma L inverse sigma R, so by virtue of the fact that you know each one of them like either commute or anti-commute, then you get. So I'm not, this is not going to be a full proof of the thing, but just enough for us to believe that this is Pauli group. This big subgroup of this G, in fact, G divided by G0 is going to be ZK, or like the cyclic group of order K. So it's really a big subgroup of the G. And another thing to notice is that sigma I by conjugation, if sigma I acting by conjugation on these guys is going to leave the subgroup invariant. It's not too difficult to see that. Like if I conjugate sigma J inverse sigma K by any sigma I am going to get something that is still going to be in G0. So in other words, sigma i's are normalizer of G0. And we're familiar with normalizers of the Pauli group. They are the Clifford group. So all you need to do at that point is to show the existence of an order K element in the Clifford group. And you can do that. Okay? So to construct a representation for this. Okay? All right, so that's, we're right on time actually. Okay. Yes.
I'd like you to recap what you said about the when you drop 3 and instead of go with 1, 2, 3 prime, you said.
Oh yes.
So the rounding there would essentially be, dropping D, like in that UD.
Oh yes, sure. So there are two things. Exactly. So if you have an operator X, any operator X, and you write down its singular value decomposition, which is going to give you two matrices U and V, which are going to be the singular vectors and the singular values, right? Then X minus U star V in Frobenius norm is going to be less than X minus Y, where Y is a unitary operator. So suppose X is any operator. You want to know what is the closest unitary operator to it, right? Well, the answer is that you drop the D, and that operator is going to be the closest thing.
Yeah, sure, but again, as you probably mentioned, it's not clear that closest unitary in Frobenius norm is also the best in terms of the cost function.
Exactly.
So,
because do you see a Frobenius norm here? Exactly.
Yeah,
it is kind of, yes.
Okay. So what were you saying about what the approximation ratio?
Oh, the approximation ratio for this, I think it's 3/4, which is not as close as, Yeah, but there is a way to fix it. And in fact, the randomized rounding that I was saying that we hope that we can prove that it's going to achieve a 13/15 approximation ratio is a way of salvaging kind of like the linear algebraic rounding method. But you just sprinkle randomness on top of it. Just very much like Goemans-Williamson's rounding scheme. Yes?
Okay, so this is a very ill-formed question. But, how do you think about these things and where you are, and in terms of like, are you, so from the outside it looks like a little bit like, okay, well there was this representation that happened to be very important, there was a choice here to use 3 or use 3 prime, but some of these things seem a little bit non-principled maybe, or sort of try them and see what happens from the way you presented it. So I'm wondering now that you've sort of had is there an analogy that you can make as to where you, it's a very open-ended question. It's sort of like, how do you see this? And are you seeing this as somehow it's the underlying structure of these groups that are being sort of pulled out and dealt with, or is it like that the groups are a tool and that eventually 10 years from now there's going to be a much different way to see what, like it's very principled?
Right. Oh, well, yes. As you know, if we could have 1 to 4, that would have been the most principled approach to it, right? There would be no question, right? But, and, just choosing one over the other, that's the kind of part that is not principled, right? And it could be that, why not even a totally different algebra, right? So that's the thing. I'm suggesting that it could be that you have to make a choice. You have to choose an algebra. Here I gave 2 different algebras that could work, right? One of them, generalized Val-Brauer. The other one, I call it generalized Clifford. And I demonstrate to you that these are the approximation ratios that you can get, right? But make no guarantee that there could be some other algebras that could achieve something better.
Is it clear you have to pick an algebra as opposed to like having an approximation to these relations? Like,
Yes, you could do that, yeah. You could, you could try to come up with an approximate representation of these things, but then these are so inconsistent with one another that when you even set n to be equal to 2, there's no hope to kind of satisfy it. But yes, approximately, maybe you could have something like that, and then, in fact, okay, so maybe I presented 2 extreme points of it. Like you can imagine that you could get maybe lambda weighted this and 1 minus lambda this, so a convex combination of these relationships, and so does that make sense? Like you could have like that this times lambda plus this times 1 minus lambda should be 0, okay? And then hope to, there you can find a representation. There you don't have any problem, right? So for any value of lambda, you probably would be able to, except for these extreme points where there's 0, 1, right? But yeah, good idea.
So we have a break till 3, and then we have our final talk by John.
Okay.